My name is Ahmed Sanaullah. I'm a senior data scientist with Red Hat Research. Joining me is Jason Schlessman, who is a principal software engineer also with Red Hat Research. Today we're going to present on CoDesign in action. What do we mean by CoDesign? Imagine you have an application that you want to optimize. You could modify the source code, maybe link in more efficient software libraries. But imagine being able to reach down to the hardware stack and customize it, so that that hardware stack is tailor-made to make your specific application run as efficiently as possible. Sounds pretty complex, right? But imagine if it wasn't. Imagine if it was possible to do that in a more productive, practical, and accessible fashion. Well, that is exactly what the research we are doing as part of the Dynamic Infrastructure Services Layer project aims to do. It aims to make FPGA programming more productive, more practical, and more accessible. So let's look at the presentation. We're going to talk about the value of our edge research to Red Hat. We're going to look at the value of FPGAs in particular, why FPGAs are so difficult to use, what is the Dynamic Infrastructure Services Layer, and then we're going to demonstrate the value of DISL by building a custom wireless security system using off-the-shelf components. So what is the value of our edge research to Red Hat? Well, there are three major buckets here. First, defensive posturing in existing markets, then expanding into newer markets, and then helping customers and partners also do the same. The one thing that I want to highlight here is lock-in backpropagation. In the absence of open source options, if we are to use proprietary alternatives at the far edge, then they can lock you into a stack that extends from the edge all the way up to the cloud. And that will limit the flexibility, the usability, and the features that you have available to you when you're using that proprietary device. So in the world of far edge devices and specialized hardware, where do FPGAs stand? Versus microcontrollers, they give you a lot more flexibility on how applications are deployed. That means more connectivity options, higher energy efficiency, better performance, and it's pretty difficult to lock you into a software stack. Versus ASICs, because FPGAs are off the shelf, it's faster time to market, it's cheaper for small numbers, you have a lower risk of over-specialization, and you also are difficult to get locked into a software stack. And FPGAs don't have to replace ASICs entirely. You can use FPGAs to augment the ASIC development process by using FPGAs to emulate the ASIC and test software while your ASICs are getting developed. So with all the promise and value of FPGAs, why are they so difficult to use? Part of it is closed source tooling and the disadvantages and limitations that are similar to pretty much any proprietary and closed source software stack. But the unique challenge with FPGAs is that when you are developing your custom stacks, you have two different development cycles that have to come together. You have the software development cycle, which has its own limitations and requirements and overheads and expertise. And then you have the hardware development cycle with its own requirements and overheads and expertise. And when that has to come together, if it's not done correctly or properly, it can lead to a very inefficient development flow. So you solve the closed source tooling problem by having open programmable hardware. And the advantages there are similar to the advantages of having any open source software. You solve the development challenge by using DISL. So what is DISL? You can think of DISL in three parts. The first part is the system configuration interface to the software developer. And this basically says you develop your custom software stacks, whether that's domain-specific languages or abstractions or some generative AI maybe. Whatever you do that works well for your workflow, stick with that. But all of that should get parsed or compiled or boiled down to this configuration file. And if you can do that, then without dealing with HDL, you can create a highly flexible and customized hardware system. For the hardware developers, it exposes an interface that allows them to package their IP blocks in a way that makes them more conducive to modifications and customizations by the software developer. And then finally, there's a system builder which takes all this in and generates for you ready to compile hardware files and the supporting software. let's look at the three parts in a bit more detail. The software interface, the challenge here was that we don't want to have just a random assortment of variables and their values, because if we do that, then this will work for some applications and not for others. What we have done with the system configuration is try to encode within this the hardware development process minus the HDL. So you're able to generate a majority of potential hardware stacks without ever having to touch HDL. On the hardware side, we take traditional IP blocks, which are rigid and difficult to modify and have fixed functionality, and we split that up into different parts, part of which will remain inflexible, but that's inevitable. But then there will be parts that you can customize, and these could be not just your basic, SIMD units, but this could be something as complex as protocol stacks like PCIe and network interfaces and DRAM controllers. And then you also have pieces where you take your HDL specific parameters and you map them into a space where when you modify parameters, it's very clear what that modification will result in the underlying hardware stack. And because we've done it this way, you get a lot more portability for your IP blocks as well, where you can support multiple other potential boards with greater hardware reuse. The third part, System Builder, really just pulls in all this information, adds in some context of definitions, and then generates out the hardware for you, which is ready to compile and then use. So we want to demonstrate the value of DISL, and we're going to do that by building a custom wireless security system using off-the-shelf components, and at no point are we going to touch HDL. So what are our requirements? We want no vendor cloud lock-in, we want low-cost off-the-shelf components, we want to use open source hardware, IP, and software tooling to the greatest extent possible. We want highly flexible design that can be customized to meet performance and energy constraints. We want to wirelessly reconfigure the FPGA, reprogram any running soft cores on it, and communicate with the application. And finally, we want to provide a secure design for managing devices in the field, because we might be demoing one device now, but you could have 1,000 of them, or maybe tens of thousands of them later on. So what you'll see in this demo is open source tooling and IP blocks to the greatest extent possible. You'll see multiple FPGA boards. You're going to see multiple hardware types, each in a role where it provides the most value. And what we've done is we've split the demo into two parts. Part A, which I will cover in a bit, we'll do the co-design, trying to build up the application. And then Jason would talk about part B, where because we have DISL and we're able to have the flexibility of how we construct our system, we're able to do more complex interfaces than just connecting the FPGA over a wire to a desktop PC. So part A, generating and optimizing the hardware design. This is our hardware setup. Got a couple of FPGA boards, a couple of camera sensors and temperature sensor, and a power meter in there just to make sure that we are energy efficient. So we want to highlight that you can build your own abstractions on top of DISL. And so what we've done here is we have built this web UI that allows us to quickly, within seconds, generate a custom system on chip and then modify it later if we need to. This is the SoC that we're trying to build. It's a RISC-V soft core that's hooked up to an I2C bus, a GPIO module, a debug port, a timer module, and then a programmer to program the soft core, and a chip manager that controls between programming and running the application. And the first part, we just hooked on the temperature sensor. So let's run through the first part of the demo, where we're going to use that web application to generate, compile, and do an initial test of our system. So you could use this interface to manually specify the different fields in the configuration file, or you could use the SoC builder utility, and within a few seconds, you're specifying the project name, what board you want to target, what soft core you want to use, what's going to hang off that soft core, and then any system parameters that can't be inferred. You hit generate, and we have a system configuration file. So we can go straight to build, we can click generate, and DISL does its thing, and we now have all of our hardware files ready to compile, so we click compile. So while that's going to compile, it's going to take a few seconds. Let's go back, and if, let's say, this system that we generated was not exactly what we wanted and we wanted to customize it, well, we can absolutely do that as well. So we can add in more modules if we wanted to support something else. We can take any module that we've already instantiated, and we can pick any of its parameters and modify them, and then we can go back and regenerate and rebuild. Or if we have a soft core, we could also then modify the software stack for it that will be used for compiling code to the hex files to run on the soft core. Or on the hardware side, we could modify its memory map if you want to add more modules to hang off the RISC-V core, or we just want to change the address mapping from what it was done by default. We can absolutely do that. Then we have custom signals. These are like intrinsics in software, things that the hardware can do very easily, and so don't really need a full module to do, things like bit manipulation and latches. And so this just allows us to quickly specify something like that without having to go through the process of building a whole IP block for it. Then you can connect things together. You can have static connections where one interface just talks to another interface all the time. You could have dynamic interconnects where you could have certain conditions under which two interfaces talk, and then a different condition where other interfaces will talk, like the programming. And then you can also have memory maps like you're seeing here with the CPU talking to the cache, debug, and other modules that it's hooked up to. And there's the example of the CPU and the programmer talking to the cache. And then here you can see an illustration of the system that we have built. And as you can see here, when the reprogrammed signal is 0, we are having the RISC-V talk to the cache. But when it becomes 1, then the RISC-V gets disconnected, and then the programmer goes in and uploads the program into the cache. And then finally, this is a hardware-specific concept. It's called overrides. The basic idea here is when you connect to interfaces, a whole bunch of signals get connected. And sometimes you want to override some of those signal connections. Maybe you want to hardwire something to 0 or 1, and this just allows you to do that. So we're at the second last step of the compilation process. We're doing the routing, which is to say that we have placed all our different logic blocks on the chip, and we're just trying to figure out an effective wiring strategy so that we're able to connect everything out and meet timing constraints and have our system run efficiently. We're now at the last step, which is writing out the bit stream, and this is I have created my system, and now I'm going to translate all this mapping that I've done and routing that I've done into a binary file that can be uploaded onto the FPGA. So it just should take a few more seconds, and there we go, we're done. So we now have a compiled binary. Let's write a simple application to run on the soft core. And so we're going to do a basic hello world. And so we're going to basically write completely software-based implementation of this. And this will get uploaded and run on the FPGA. So we're going to do hello world without actually writing hardware beyond what we just compiled. So we compile the software application, and this is the Python script that's going to run on the host. And what this is going to do is it's going to use our custom JTAG stack to program the FPGA, to configure the UART port. It's going to then clear that UART buffers. It's going to program the soft core, and that's going to pull that UART port to see if something comes over from the FPGA. So we're going to run that, and we have our hello world. Pretty cool, right? We run an application without actually writing the hardware for that specific workload. So let's do something a bit more complex. Let's, again, without changing the hardware, let's now read the temperature sensor. And this is going to be complex. This is not just, here's the temperature value out. No, we're going to read some data, we're going to process it, compute the temperature value, and then print it. So we pasted in the code for that, we compiled it, and now we're going to run it. And it's going to go through the same steps of programming the FPGA, programming the soft core, and we have our temperature value. So let's extend this concept a bit further. We want to build a wireless security system, or we want to build a doorbell camera. So what do we need for it? Well, let's do the most basic implementation first. Let's just only have the SPI controller and hardware, and implement the entire library for interfacing the camera module in software. And this is something we ported over from the RGCam library for Arduino, and we just replaced the low-level functions with our FPGA specific or software specific function calls. So for JPEG capture, we were able to get the image out in 1 second. But we do want to process this because we are building this wireless security system. And so to do any local image processing, we need the raw pixel data. For that, we need to capture RGB images. Just by modifying the soft core, we were able to get that out. It took 7 seconds, which was 7 times slower, but that's because we're capturing a lot more data now. And then where this problem got worse was when we tried to do edge detection as well. Also in software, we were able to do it, but it took 24 times longer than it was to just capture the JPEG image. And you can see that's because the processing time here has gone up quite a bit. So maybe we can do something to improve this. And by virtue of being on an FPGA and having a RISC-V core, we can just use a custom instruction. So what we did was we implemented a systolic array that's going to hang off the soft core, and it's going to be interfaced by a custom instruction. And so this is where we were, 24 seconds runtime. When we offloaded the processing to custom hardware, we now get it down to 7.5 seconds. So that's like 3.2 times faster. And then, we're doing this overlays for illustrative purposes. What we really need is just a binary image. And if we modify the soft core without changing the hardware, we get up to 3.4 times faster. It's better, but not quite where we want to be. So what can we do? Well, we can offload something more complex to hardware because, again, we're on an FPGA and we can do that. And so what we do is we add the capability where you can not just process, but also capture and transmit as part of the custom instruction call. So before, when we were doing capture and transmit software, we had a 7-second runtime. Then when we offloaded capture and transmit to custom hardware while still capturing RGB images, we get 0.3 seconds. We're like 23 times faster now. And instead of now capturing RGB, what if we capture JPEG and decode it as part of the pipeline and then use that image? We can get 54 times faster than we were when we were doing capture and transmit purely in software. So we have gone from 1 second JPEG captures to 0.13 second of not just capturing, but also processing and also transmitting. So we have now really improved the efficiency and the performance of our pipeline. So can we do more now that we're on an FPGA and we have this pipeline up and running and we can write softcore code? So why not deploy a convolutional neural network? So how do we do that? Well, we train it, then we quantize it, and then we implement the CNN computation as part of the softcore code. So what do we get? Well, person detection. We can now see if there's a person there or if there's not a person there. It's pretty slow though, right? It's taking about 5 seconds to capture the next frame. Can we do better? Absolutely. Because FPGAs. We can just buy another FPGA off the shelf that's got a little better performance potential because maybe it has a faster oscillator. And we can do optional improvements to the SoC. These are not necessary, but just to show that we can modify the design and everything just doesn't break, we added in DDR support as well. And so when we were running on the CMOD board, which was a 12 megahertz oscillator, it was 5 frames a second. When we switched over to the RD board, which could supply 83 megahertz to the Pico RV core, we got it down to maybe a second and a half, a lot faster. And then we modify the soft core so that instead of doing every iteration a capture, process, transmit, we do a capture process. And then if we detect that there's a person, then for 10 frames, we just do a capture transmit. So we get an even better frame rate. And now imagine not having to transmit the image at all. If you detect a person, just transmitting 1 bit, a person or not a person, just imagine the performance we can get, and just imagine the energy efficiency we can get by not having to transmit entire images and just that 1 bit back to the user. And so for the second part, I'm going to hand it over to Jason, who's going to take all this stuff wireless.
Thanks, Ahmed. So as was pointed out, in this part, we are looking into how to access and manage these devices. As was said earlier, we expect to have hundreds, thousands, and perhaps tens of thousands of devices in a fleet deployed on the edge or perhaps in areas where access is not feasible. So we can't expect to have a USB connection to our device, connecting it to a PC, allowing us to monitor and update and, in some cases, reconfigure or reprogram. So beyond that, we also have to consider that when we're using, as we increase the number of devices, we have to also take into account that we want to reduce both our energy footprint and our financial footprint, because scaling those up, when we cost more in terms of how much energy we're using, that reduces the amount of time that our devices can be active doing what we want them to do. And the financial aspect just is pretty obvious as you're scaling up. So how did we go about doing this? We first looked into keeping the FPGA as a standalone device that would have a processor that we called the communications processor attached to it via a physical connection. In our case, we were using USB. However, as the way that we view this is that the comms processor is a drop-in. It's something that can be swapped out. So if one is using legacy hardware, or one has a microcontroller that they prefer for whatever other features it carries, as long as it has a way to communicate with the FPGA, perhaps over UART or CAN bus, we expect that this architecture will still be viable. Beyond that, in order to have remote access, we need to have a radio of some sort. That could be Wi-Fi, or it could be LoRa, it could even be BLE. And so for our case, we used an ESP32S3 microcontroller from Espressive. And we're utilizing the USB for that. That device has a USB host controller built in. And then it also has both Wi-Fi and BLE, but we're using the Wi-Fi for it. So when we talked about having a secure infrastructure and having an enterprise architecture, we envisaged that we would have some secured network that would handle, we'd have to have a database to keep track of information about our devices. We'd need a file server that would be secured to keep, shall we say, glacial files, stuff that we want to keep long-term records of how the devices are interacting and behaving. And this could be log files, it could be updates. And then we expect to have at least two user interfaces, one for status that users could get at, and the other would be for admins to actually make modifications to the devices or do debugging or troubleshooting. We expect that the devices would not communicate with the secured infrastructure network and instead would communicate over a message broker. And finally, that there would be a file server that would also be on an outward-facing network for the devices to get things like configuration files, parameter files, the bitstream files that were mentioned earlier for the FPGA, and the hex files that were mentioned earlier for programming the soft core. Now, this is what we envisaged. However, what we actually have implemented thus far is a demo or proof of concept architecture. So we have a PC, and on it is running a Postgres database. We're using the Mosquito MQTT broker partly because of its ready availability and because it is an open source solution. And we have a simple Apache file server running on this PC. We did not make multiple UIs. We made a somewhat universal UI for controlling the devices and monitoring them. It's a Python GUI that I'll show in a later slide. And then for our purposes to monitor the traffic over the network and the message broker, we took advantage of an existing open source tool called MQTT Explorer. So without going too deep into how MQTT works, we'll just say that MQTT is built around the concept of having a topic. and it's very flexible. One can pretty much arrange their topic tree however they like for their system or application. What we chose to do was to have each device have a unique identifier, calling in here its device name, and each topic is prepended with that device name, and then after it is the specific information that gets transferred across the topic. So we have a heartbeat topic that every 5 seconds the device sends out just its uptime, and that's the 5 seconds is pretty quick. It's usually spread out further, but for our testing purposes, we kept it at that. We have in command and out command. So the in command is for messages to be sent to the device to tell it basically what we want it to do. And then the out command is for the device to send its responses in terms of what the results were of attempting to service the command that was sent. Beyond that, we also have a means for doing data communication, as was mentioned as one of our requirements earlier. So we left things, again, with the comms processor such that it is more of a pass-through as much as possible. And what I mean by that is we want the FPGA and softcore applications to dictate where the information goes. So as we can see here, we allow the softcore to send a JSON message that gives a field for topic and then a field for message. And so upon the comms processor getting this and parsing it, it will then send whatever is inside the message to the device's topic, given whatever's in the value area for the topic field. And that way, if you think about it, all sorts of information can be sent out. It keeps things really open-ended and flexible. So I mentioned the UI we put together earlier. This is distinct from the DISL UI. We might integrate them in the future. But for now, this is a standalone UI, and it gives the ability to provide the MQTT broker information and connect to it. And then there's a device drop-down area that gets populated by the Postgres database that has all the information about the devices. Over is a device status area where we can get information from the device once we connect to it, as far as what comms processor firmware version is running, if messages are coming from the softcore as far as its firmware version. Once an FPGA bit stream is sent over via the controller, then information about that will be listed, same with the softcore. And for the doorbell and the temperature applications, information about those will be listed here as well. So we mentioned earlier about having a file server. And so the idea here is that we want to be able to update either the softcore or the FPGA itself with hex files or bitstream files, respectively. But we need a way to actually get those files to the comms processor. So there is a file system attached to the ESP32S3 in our proof of concept. And by giving a URL where a bitstream or hex file exists, we can then instruct the comms processor to download the file from the URL to its local file system. Once that's all in place, we then at the bottom here have the ability to reconfigure the FPGA by giving a file name, and the same deal, reprogramming the softcore by giving it a file name. And so I'm showing this demo board, which is very similar to the one that was shown earlier, but since this is the one that's going to show on the demo videos, I felt it prudent to mention it. So we'll have the Argicam at the top here, and then I'm using the CMOD 87, which is the FPGA that provides the slower oscillator, which will be important when we get to the doorbell part. And then the ESP32S3 is at the bottom. We have an OLED display that will display the heartbeat message that I mentioned earlier. Again, it was a way for us to just verify uptime. And then finally, in the lower right, we have the micro SD card, and that's attached to the comms processor, and that's where the hex files and bitstream files get stored. So the first demo that we're going to show is just to demonstrate remote programming of the FPGA. We're not getting into the software at all here, and we're not using sensors, camera, nothing of the sort. We are simply going to take two different bit streams. One will blink one LED, and then the other will blink two LEDs. And we're going to use the controller UI to reconfigure these, and one at a time. And we expect to see first single LED blinks and then double LED blinks. So here we go. So starting out here, and I'm putting in the name of the MQTT broker, connecting to it. And this is the drop down that I mentioned earlier. And I'm selecting my device, and you can see that the device status, the device commands that are available, and the device files all got populated. So currently, we have no information on the status other than the comms processor firmware. And here I'm showing that there are a number of device commands available. We're not going to use those in this demo, but the idea is that one could extend the comms processor by adding more commands. And a lot of these commands are called by the controller, like the get version command is called. So now we're going to reconfigure the FPGA with the single blink.bin bitstream. I clicked reconfigure. You might have seen that the LED on the FPGA went out because that indicates that it's starting the program. And then in the status section, it now indicates that it's updating the FPGA to the single blink bitstream. And now if you, it's a little difficult to see, but now there is an LED blinking on the CMOD. So next, we are going to program double blink or db.bin bitstream. And it's going to be the same deal. We're going to click reconfigure, and already the status is saying that it's attempting to update. The LEDs are the LED is not blinking, and the main LED is not on because it's programming again. And once this finishes, we expect the device status to update, which it just did. And now we have the main amber LED on, and then we have two other LEDs blinking, thus showing that we were able to get the FPGA programmed in a wireless fashion. There is no USB connection to a PC or otherwise. Now we showed that we were able to update the FPGA. And while that's pretty huge, because that means that we can put our devices out there, we can put different configurations of the hardware in place without having to have physical access to the hardware. We also saw previously how important the softcore, the RISC-V softcore, ends up being in terms of some of the application aspects. So we want to be able to program that as well. And for this demo, we take a bitstream that supports the RGCam, and it'll have both a SPI and an I2C connection, just like what was talked about in Part A. And we expect to see detection status from the device, either detected or not detected. So once again, we will go into our UI, and you can see that the amber LED on the CMOD is back on. We no longer have the previous demo on here. We are going to reconfigure with the CM cam bitstream. And so we see once again that it is updating to that. And once that finishes, just like before, we expect the FPGA file status to change from updating to just the file. Now that's happened, and you can probably see that there's a very bright LED that's on right now, and that's specific to the CM-CAM bitstream. So now we're going to reprogram the softcore. Same deal. You probably couldn't see it because it was so quick. But the softcore went from updating the cmcam.hex to cmcam.hex. You can see the softcore firmware has updated to 0.19. And in this case, the doorbell has detected me because I'm standing right in front of it. Now you'll notice my hand is going across the Argicam so that it can no longer see me. And there it went to no detection, but I'm going to point out that since this is the 12 megahertz oscillator FPGA, it does take, at least the 5 seconds that was mentioned earlier for detection cycles to go through. So now my hand is away, and I'm looking at the camera again, and now it's detected me again. Now we've shown that we were able to implement the wireless doorbell security system that we set out to do. And what was innovative about this work? Well, first of all, DISL makes it possible to do co-design of hardware and software for FPGAs. And for hardware folks, FPGAs are just considered, straightforward mostly and accessible. The problem becomes when software folks need to get involved, and we do need to get involved because co-design, mandates that there's a hardware and software component. But the beauty of DISL is that it lets us focus on application development. So if we're working on the software side of things, we know that there's a hardware component, but we don't want to have to get into HDL. We could probably do it. We could figure it out, but DISL makes it so we don't have to. And it makes things quicker and more consistent. And so beyond that, as we just showed, the demo gave us an example of how to use DISL to make interesting systems that take advantage of hardware acceleration, but also we added the ability to manage the devices in the field with remote access. We're able to update the FPGA, update the softcore, as well as send just general data information from the FPGA over a wireless interface. And then on top of that, as you saw, our demo showed user interfaces that are proofs of concept examples, but they demonstrated that we were able to have simplified system generation and device access, monitoring, and management. Beyond that, the demo code that we've shown is available, and we encourage everybody that's interested to contact us. And you can contact us at our email addresses that are on this slide. Also, as part of Red Hat Research, we have other projects that are just as interesting as this one. We have Red Hat Research Days events where we talk about those projects, and we also encourage everybody to sign up for Red Hat Research Quarterly publication, and we have research interest groups that we encourage people to check out.